So by the time you get back to the classroom, or if you're in the classroom, you should have done an intro torque lab, right? So with the introduction of torque, what you guys did was you had like a watch glass and a ruler or a meter stick, and you started putting masses on each side to see how you can balance it. And the most easiest way to do it, is put equal mass, right? So I could put like a 3 kilogram here, and I could put the same distance away, right? This is a distance D. I could put from that same distance from the center another mass of the same mass, right? So same mass on both sides. But it was also possible to have different masses on each side. So, I don't necessarily need to have a 3 kilogram same distance away. What I can do instead is I can put a 1 kilogram mass farther away. I could still have this thing balanced as long as I put the 1 kilogram mass farther away, or bring in or probably in addition to bringing the 3 kilogram mass closer. So you could do that. You could even get something like this, right? You could get all of your mass on one side. Let me draw it out. You could have gotten all of your mass on one side and still have this balance, right? If I put all my mass on one side, I could still have it balanced as long as I had the ruler, as long as I shifted it so that the mass was much closer to the watch glass while the ruler was longer on one side. So there were many ways you could have balanced it. And what you probably noticed, or I guess, yeah, like what you noticed is that the mass doesn't need to be the same on each side, right? Like if you think about the forces on this side, right? So the forces on one side, well, this side, we have Fg. We have the force of gravity on the ruler, which, acts at the center of mass. I think you might have learned that in Unit 3 or gravitation unit. If you didn't know that, it's you can do that, right? If it's uniform, well, not if it's uniform. Fg always acts at the center of mass. If it's uniform, the center of mass is in the middle, right? So Fg acts on the center of mass, and you have these forces right here, not necessarily Fg, right? Like you intuitively you'd be like, well, the force on this side is mg, 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 right? But remember, when you're dealing with forces, it's a force between two objects. Really, it's the force by the mass pushing down on the ruler, like an Fn, right? But when you do when you think about, well, this Fn points here, that's going to equal Fg. So these forces are equal to the weight of each object. They're just not necessarily the weight of each object. Hopefully that makes sense. My point being, you could get way more force on this side compared to very little force on this side. Because this meter stick is like, what, 2 grams or something? I don't know. It's really small. So you could get balance happening even with completely different forces on each side. So if the forces aren't the same on each side, what is the same on each side that is causing this thing to be balanced? That balanced quantity is torque. So I'm going to call it torque. I'm going to call it that. I actually just invented this on the spot. No, I'm just kidding. It looks like a French word, honestly, so maybe it's a French thing. But torque, that's the quantity on this side that is the same as on that side. So that probably doesn't give you a good idea of what torque is, but that's just showing you how things aren't intuitive, right? Like you'd think you need equal forces, but what you really need is equal torque. So to talk about torque, a great way to think about it is with the door. So if you had a door, so I have a door right here. It's in my bedroom, actually. You can't see the door, so I don't know why I demonstrated that. But if you had a door, and you were to look at it like from the top below, so if this was our door handle, right? You have a door. The doorknob's always farthest away. Why? Well, if, let's say, in order to get this door open, you got to apply a certain amount of force. I'll call it force F. And you could apply that force really anywhere, right? But we apply that force at the very end Because if you were to try, right, like if you're watching this right now in your bedroom, you could open up your door. If you try closing it from the, you can even hear me like struggle with that. Oh my God, there we go. You could apply the force near the hinge. It's gonna feel really hard. If you do it at the end, it feels much easier. You know, and really, you know, what's happening is, you would be applying less force here because it's like, you know, you're trying to get a constant angular velocity and there's like frictional torques. Whatever, the point is the closer you get here, the harder it's gonna feel. That's the idea with torque. Torque is like rotational force. Torque is not a force, but it causes rotational acceleration in the same way a force causes linear acceleration. So you can get things to rotate with a torque. So I'll say torque is like rotational force, but it's not really a force at all. Like dimensionally speaking, because of the units and stuff. It's not a force, but forces can produce torques, and those torques cause rotation if something's not already rotating. And hey, if something's already rotating, you can imagine it's going to keep rotating, right? So Newton's laws are kind of analogous from linear motion to rotational motion. And we'll talk about that more as the unit progresses. But for right now, torque is like rotational force. So going back to this example, right? If I have a box, right, and I don't want this thing to move, I gotta have no net force. So if I apply a force here, you best believe there better be another force the opposite way so that it nets out to zero and you get no motion. And like, that is analogous to what's going on over here. I don't want this thing to rotate. I don't want this meter stick to rotate. So there are two torques at play, right? So when you're dealing with torque, you got to think about what is your axis of rotation, the axis of, and we'll talk more about that when it comes to problem solving, because it's really important. But the whole idea of axis of rotation is where will the rotation occur, right? And right here, it's pretty clear that, hey, the rotation will occur right here. So I'll mark that my axis of rotation. It is literally like an axis going through the page. It's going to rotate like about that point. So there are two torques. There is a torque on this side, the right side. Yeah, I write with the right side. Torque on the right side, balancing out the torque on the left side. Just like how these two forces have to balance each other out, these two torques have to balance each other out. So I'll say this: torque on the left side minus the torque on the right side equals 0 Newton meters. And yeah, that's right. That's the unit of torque, Newton meters. Torque is not energy. One of my favorite memories ever is one time I was in class, and I think like there was a girl. This was an AP Physics 1. There was like a girl next to me, and my teacher, Mr. Fitz, was like, the units are Newton meters, and I was like, oh, doesn't that remind you of energy? Like, I was talking to that girl, like, oh, that's like energy, right? And then Mr. Fitz heard me, and he like called me out. I was like, Frisch is so wrong. This has nothing to do with energy. I still think torque has some connection to energy, but whatever. That's a video for another day. The whole point is that's the units, and when the torques are balanced, the net torque is 0, right? So T net is equal to 0. Torque net is equal to 0. So yeah, torque left and torque right have to balance each other out. And yeah, one of them is negative, right? Because torque also has direction. Direction for torque's more... It's funny, right? Because these forces are both downwards and they're producing torques in the opposite direction. It's pretty simple, honestly, to figure out which direction your torque is causing rotation for, right? Like, you just put, if this was your board, you could see this force is trying to create a torque that wants to produce motion clockwise, right? Like this force is trying to cause, or I guess this torque is trying to cause clockwise rotation. The torques here are trying to cause counterclockwise rotation. So one of them is negative. I think the convention is counterclockwise positive, clockwise is negative, but just like, you know, you could say the left side is a positive force, the right side is a negative force. It's up to you as long as they're opposites of one another, right? So torque left minus torque right equals 0. Let's talk about the equation for torque. So if you want to calculate how, and you did a lab on this, and you could linearize your force versus distance graph. Maybe I'll make a video on that if you need. But the equation for torque, just to simply put it, is equal to force, so the force being applied times the distance from your axis of rotation. So how do I want, if I want to find the torque produced by the weight of the meter stick, I just need a rule. Well, I can use a meter stick actually. How cool is that? You can use a meter stick itself to find the distance r, not radius, but distance r from the axis of rotation. Multiply by that by Fg, and you get the torque produced by by the weight of the meter stick. And hey, that torque is equal to that torque. So what I can do is, for a seesaw problem, which are going to be coming at you real soon, if I know, let's say this meter stick, let's say I balance it like so, right? And then I put a 50 kilogram kid here and a 70 kilogram kid here. Hopefully it makes sense why the heavier kid is closer to the seesaw fulcrum, or this point thing, and that's our axis of rotation. I could say, well, hey, the torque by the 50 kilogram kid, remember, because the kid itself is applying a force pushing down on here, minus the torque by the 70 kilogram kid equals 0. So the force of the 50 kilogram kid times its distance, R1, is going to equal, right, if I add on both sides, the force by the 70 kilogram kid times R2. And force by the 50 kilogram kid, remember, as I was kind of talking about here, the 50 kilogram kid is pushing down like so. That equal and opposite force by the seesaw pushes back up on the kid. And if the kid is not accelerating, that upward force has to equal, it's Fg, right? So the Fg on the kid is equal to the Fn, and that Fn is equal to the force pushing down. This ends up being mg, right? So m1 g r1 is equal m2 g r2. So if I know one of the distances and their masses, I can figure out the other distance, right? So this is kind of like setting up F net equations to solve for unknown forces. You can do the same thing with your torque net equation. There is one component to this equation that we are missing. And we'll talk about it. And if you want to maybe think about what component of the equation we're missing, try opening the door by pulling this way. Thank you for watching. Hopefully this cleared up some things about torque or gave you a good intro to it. I'll make some more videos soon about this stuff. Thank you for watching.